Okay, my name's James Norton. I'm going to talk to you today about the Gemini SDK. It's an iOS 2D game development environment that I've created mainly as a learning experience over the last year or so in order to learn a little bit more about Lua and Lua bindings and to facilitate some of the development I do on the iOS platform. Okay, Gemini. Basically, Gemini provides Lua bindings for 2D game development. It allows games to be encoded entirely in Lua or a mixture of Lua and ObjectiveC. And it basically consists of a set of C libraries and then ObjectiveC project code and templates to make it easier to just jumpstart right into a project. It has an API very similar to the Corona SDK, if any of you are familiar with Corona development. Basically another non-open source framework that provides a lot of facility for developing applications for cross-platform mobile devices. Gemini is open source. It uses the MIT license. I'm basically developing it as a learning experience, but trying to do something that actually is useful as well. Okay, why would you use scripting in order to do game development? I'm probably preaching to the choir here, but basically, first of all, it provides a much higher level of abstraction, so you can be much more productive than you can when you're working in low-level code with OpenGl and ObjectiveC. Secondly, level designers and non-programmers can get in to use Lua and it can write scripts that don't involve a lot of technical and programming skills. So if you work on a team, it makes it very easy for your level designers and your non-programmers to get involved. Another plus that isn't highlighted very often, but is actually pretty important, is that if you use scripting, in particular Lua scripting, in order to do game development, you can change all your assets and not have to recompile your executable. So you can make changes to your levels, make changes to your graphics, whatever you want, and load those assets externally during development without having to rebuild the executable every time. So if you have people on the team that aren't actual developers, they can make changes and see how those affect the outcome without having to rebuild things. The features of Gemini. Gemini uses a 2D layer-based rendering, which if you've used any kind of modern drawing program like Photoshop or Illustrator, you're probably familiar with the concept of using layers in order to render things in sort of a painter's fashion. It's event-driven, unlike straight OpenGL coding, where you essentially are writing code to redraw the frame every single frame loop. With Gemini, you basically set up your assets and you write event handlers to handle certain things that happen whenever people interact with the objects. It provides a ton of graphic elements, and I'll go over those. It provides a physics API, so you can add physics to your games really easily. Every graphical object can have physics attributes and can be, things can bounce around and realistically and add a lot of realism to your games. It provides sound, so you can have sound effects, music, kind of typical things you would need for game development. It provides a scene management API, which allows you to easily set up things like levels or scenes and to move back and forth and transition back and forth between those. Which makes it easy to write modules for each level and have things split up in a sane way. Now, going back to the layers, basically there's a set of things that are provided when you use a layer-based approach. For one thing, you can give yourself a sense of depth. Even though we're talking about 2D games here, you still, in a typical 2D game, you have some sort of sense of depth. You have a background, you have a foreground, you have characters running around in the foreground. So layers allow you to add that very easily, because each layer has an index, and based on the index, you sort these layers and they get rendered on top of each other. This allows you to do things like a parallax effect, where you have the background moving at a different rate than the foreground characters, so that it gives you a sense of motion. Layers support blending functions. I'll talk more about that. So you can do all kinds of blending effects to get neat effects with your graphics. Layers are also the mechanism allow me to add a thing called render callbacks, which allow you to actually invoke direct ObjectiveC code or C code or C++ code to render a specific layer. For instance, you may have a background, you may have already written a routine that's very good at scrolling backgrounds very quickly back and forth, and you want to reuse that code, instead of having to rewrite it in Lua and trying to go through Gemini to do the same things, you can invoke that code directly as a background layer. So when Gemini goes through its system and renders each layer, it will invoke your code and just do that rendering directly. I'll talk a little bit more about layer blending. Basically, any OpenGL blending function that's available is available to Gemini. So you can set up your layers to have any OpenGL blending function that's available. Two really common examples would be alpha blending, which gives you transparency, which is sort of like looking through transparent colored glass. And this is set using, if you're at all familiar with OpenGL code, this is set using the OpenGL functions. A common example would be additive blending, which is really common with particle systems, where you, rather than having colors mixed together, colors get added together. So as particles layer on top of each other, things get brighter and brighter. So if you have explosions, you have a nice bright spot where all the particles are on top of each other. So basically, any OpenGL blending function is available to Gemini, and that's one of the things that layers by you. Again, I mentioned render callbacks. If you've done any kind of game development, you probably have libraries of functions that are written in a native language like C or C++ or ObjectiveC to do certain things. And for instance, in this case, if you have an API that allows you to easily do scrolling, you may not want to redo that in Lua code through Gemini. You may want to just say, okay, let me use that API directly and set up my background scrolling, and then everything else I'll handle in front. So in this case, you've got a background that's being scrolled with ObjectiveC code, and then everything in front with a little Mario guy running around, that's all controlled with Gemini through Lua code. I mentioned that Gemini is an event-driven system, and there are a few key events that are defined. Enter frame event fires every render loop. Again, we don't use a typical render loop the way you would with an OpenGL-based game, where you have code that executes every render loop to draw everything. With Gemini, you set up your assets, and they'll automatically get drawn every render loop by Gemini itself. But there may be things you want to do every loop in order to check state and change things on the fly. So you can set up event handlers that will listen for the enter frame event, and then every frame essentially will execute some code on your behalf. For instance, if you want to check to make sure the velocity on some object hasn't gone past some limit, and you want to pull that back, that may be a good place to do it. I have all the touch events you would expect with the mobile devices, including phases like touches began, touches moved, touches ended, touches canceled, to allow you to respond to them in however you want. And events can be set on a global level. Handlers can be set on a global level to listen to touches that happen anywhere on the screen, or it can be per object. So if you create rectangles or something or circles, and you want them to listen specifically for touches, you can set a touch listener on those, and Gemini will automatically detect if someone's touched one of those and send the event to that handler. And again, you can use the phases to determine what part of the touch was happening. Scene events are part of the Scene API, the Director API. Scene events allow you to set up a scene prior to loading it in, set up some functionality right after it's loaded in, and remove the assets after it's no longer needed. All just by setting up event handlers. And then, of course, timer events allow you to execute code after a particular delay. And there are other events, but they're not quite as important. And then, of course, there's physics events. You can detect collisions through event handlers for any objects that you set physics on. The graphic elements that Gemini provides are, first of all, sprites, and the sprite code has been highly optimized to execute very quickly using sprite batching and minimizing the number of render calls that are needed. And I guess for anyone who's not familiar, sprites are small little animations that are stored, generally for characters or anything else running around in your game. You can draw lines. In this case, they're polylines. They're actually made up of multiple segments. They have beveling in between. You can have thicknesses. It can be as thick as the whole screen if you want it. Rectangles can have borders, and circles can also have borders, and rectangles and circles can both have gradients set on them instead of solid fill colors. And then you can have arbitrary convex polygons. Gemini supports text using the text candy library, which is actually a library that was written for Corona. So basically, it doesn't have complete support for text candy yet, but it does most of the basics. You can do, you can use fonts from some of the other third-party tools that generate fonts for Corona, and do some of the effects, like in this case of drawing a text in a circle, to make it really easy to use text in your games. And then one of the last graphics elements is display groups. Display groups allow you to take a bunch of objects you've added to the scene and then group them together in a way that you can then manipulate them as a group. So if you want to set the rotation on all of them all at once to spin them in a circle, you can add them to a group and then change the rotation for that group, and it'll spin everything around. Or you can move that group in as a group, and everything will move at once, just to make it convenient for certain types of operations. Again, I mentioned that Gemini provides a physics API, and basically this is done using the Box 2D physics library, which is an open source library that some of you may be familiar with. Any graphic element that you create in Gemini can be assigned physics properties. And this includes, giving it bodies, adding fixtures and joints, and all the things you can do with Box 2D you can do in Gemini, including applying forces, setting velocities, hooking things together through joints, and all the Box 2D body types are supported, which is dynamic, static, and kinematic. Dynamic body types are body types that generally are completely controlled by the physics API. So that's normally the typical things in your game would be dynamic. Static types are types that other things can bounce off of, but they don't respond to forces or anything in any other things bouncing off of them. And then kinematic bodies are bodies that are strictly under programmatic control. Things will bounce off of them, but they don't interact with other things. You typically use this for things like sliding levels or platforms or things like that. And then, of course, there's all the collision events involved with this. So you can detect whenever you can, if you set a physics body on an object, you can set an event handler on it to let you know when something makes contact with that, and it'll tell you what made contact with that, and you can write code to respond to that. So if you have a trigger in your game, and whenever you want to know when the character runs over the trigger, you can set up a collision event, and this will allow you to Xcode at that point to do something. Again, Gemini provides sound, basically what you would need for game development. This is based on the ObjectiveAL API, which is an open source ObjectiveC wrapper around OpenAL. And I don't know if anyone's ever used OpenAL before, but OpenAL makes programming in OpenGL look like child's play. So ObjectiveAL provides a nice wraparound, and it makes it really easy. Things just kind of work. It makes it really easy to do things. Again, you get sound effects and music from this pretty simply. You just basically say, I want to load this music file. Well, now I want to play it. The Gemini also provides transitions, which is a way of sort of setting up canned effects with objects. You can say, for a given object, I want over a certain period of time, I want this parameter to change to this. This is a good way to make things disappear. You can change their alpha value so that they gradually fade away, or they fade in if you increase their alpha value. Or you can move things that way if you have something canned that you want to do that's not going to be interactive. For instance, in this particular slide, star transitions to the right with a spin. Very easy to do with transitions in Gemini. The scene management API is the director API provides basically a way to allow you to script your levels in a sane way. Instead of having one giant Lua file or trying to organize your Lua files in a way that provides loading and unloading of levels, the director API does all that for you. Basically, you have a template which is a module for each level you want to load, or each scene you want to load, and then that template is a collection of event handlers corresponding to events in the scene API. Scenes are collections of layers and all the objects within the layers, and they can be manipulated through the scene manager API by loading them in and then sliding them in and out, basically with different transition effects. So basically, you can tell with the director API, you can tell Gemini, I want to load this scene, but I'm not going to show it yet. I'm going to load this scene and show it. Okay, now transition to this other scene, and I want you to use this transition. Right now, I only provide 2 transitions: a slide transition, which moves from one scene to the next just by sliding up and down, left, right, and the ubiquitous page curl transition, which, if you've ever used an iPad, you've seen the page curl. There's a lot more room for other transitions, and there's a whole framework here for adding your own transitions. Obviously, dissolves and all the other kind of things you get with typical scene management will be coming. Again, Gemini is event-driven, and the scene management API works completely around the idea of using events. The events that are in place right now are create scene, scene entered, scene exited, and destroy scene. Create scene is executed when you very first load the scene. So this is typically where you're going to create all your assets. You're going to, the rectangles or circles or whatever you want, or sprites. You can load them there, and you're going to position them there. Add physics bodies there, but not enable any of that interaction. The scene entered event occurs when the scene gets loaded onto the screen, and that's the point where you actually turn everything on. So you would enable all the handlers at that point that are going to respond to different events. Scene exited occurs when you transition to a different scene, but you haven't destroyed that scene yet. You may want to go back to it, so you don't want to unload all the things you loaded, but at that point you're going to turn off all your handlers and turn off all your effects. And then destroy scene is an event that gets sent to the scene when you actually want to get rid of it. So you're done with it, you're not going to use it again, so you want to unload all the resources to free up memory or whatever. The other 2 in yellow are not implemented yet. I'm probably going to add them strictly because sometimes when you're doing transitions, you want to turn things on and off in the middle of the transition, and so these other 2 events will probably be added to facilitate that. You'll see some examples of transitions and see how that works and why that's kind of important. Now, again, scene transitions are different from the transitions I talked about earlier, which were object transitions, where you're just going to change the properties of a particular object. A scene transition is just moving from one scene to another with some sort of effect in the middle. Let me pull up. I just want to show you really quickly what the scene template looks like. So at the top of the thing here, you load the director API. This is Lua code, by the way. You're then going to actually create the local instance of the scene by calling new scene on the director API. And then basically down here you have set up a bunch of event handlers, and those correspond to all the events that I talked about. So in this really simple example, you've got a create scene event handler set up, and you're going to, in this case, create a new layer by calling the display API, which has all the factories for creating different graphical elements. So you create a new layer, and it's got index 1, which means it's just at level 1. Then you're going to set a blend function on it. In this case, it's just normal alpha blending, which is pretty typical. And then you're going to add that layer to the scene. Now you're going to create a new rectangle, a green rectangle here. We're going to set its fill color to green, and then we're going to give it a name. You can add names to all the Gemini objects, and it helps you, disambiguate them, particularly when you're doing debugging. Then you go ahead and insert it into the layer. So now that executes as soon as the scene loads. Then when you actually transition to the scene and it comes on screen, the enter scene event gets called, and this next event handler is set up for that. And so this is basically going to set up a, excuse me, this is going to create a listener that's going to, this function right here is basically going to add a little bit to the angle of rotation for this rectangle every time the enter scene event it fires. So here we actually add the event to our runtime. The runtime is sort of the global system. So right now the runtime gets this event listener set up. So every time the enter frame event occurs, which is going to happen every render loop, which is typically 60 times a second, this thing is going to call this listener, this function. So it's basically going to rotate a rectangle. And this is typically a terrible way to do this, because generally you don't want to rotate by a fixed amount every frame, because if your frame rate changes, then your rectangle is going to slow down. But this is just a simple example of the kind of things you can do. And then down here you have your other events. On exit scene, you're going to remove your event listener because you don't want the thing to keep firing when it's no longer being displayed. Typically down here in destroy scene, you would actually remove your rectangle and your layer from your scene, but I didn't put it in. And then down here, you actually add these add event listener, and actually these event handlers you define. This is where you actually add them to the scene, and then the scene gets returned. And so this code gets invoked whenever you say, when you load a scene, this would be a separate Lua file. This would get loaded, and then these events would get called when each of those scene events fired. All right. All right. So let me talk a little bit about implementation. Basically, it's all implemented as libraries of C methods that delegate to a bunch of ObjectiveC code. We have a whole set of ObjectiveC classes that provide all the sprite rendering and all the rectangles, all the different graphic effects, and all the event handling is all done in ObjectiveC. And basically, this is just a set of bindings that allow you to access that functionality in a convenient object fashion. All the libraries have factory methods that allow you to create the various objects. And basically, I'm just using metatables and here's the point where my inexperience with Lua may show up. If I say anything incorrect, feel free to correct me, because basically I'm using metatables to define the custom types that you use in Lua. So in Lua, if you want to create a rectangle, you say new rectangle, it's a rectangle object. And the reason the C code knows it's a rectangle object is because it has a metatable assigned to it that has been identified as the metatable associated with rectangles. So the custom types in Lua are used to wrap all these ObjectiveC objects, like the rectangles and triangles and rectangles and circles and things like that. And so basically, we can create all these ObjectiveC types in Lua using these factory methods. So when you create one of these Lua objects, it's actually in the background, it's creating a corresponding ObjectiveC object that actually implements all the functionality. And all these custom types are defined in libraries with factory methods and instance methods defined within that library. So there's one library for each set of types. So for all the primitive graphic types, there's one library called display, and that has all the factory methods for creating rectangles, creating circles, and all that kind of stuff. Sprites have their own library that gets loaded, the sprite library, and that has all the factories and all the methods that get called for the sprite methods themselves. So basically, the way this is done is I'm using using user data to get a block of raw memory for each object that gets created through one of the factory methods, and then we're going to store a pointer to the ObjectiveC object that gets created at the same time. So in your factory method, when you say new rectangle, it first thing it does is create a rectangle object in ObjectiveC, and then it creates a block of memory with user data, and then it fills it in with the pointer for that object. So basically by calling Lua new user data. And then again, we use metatables to basically turn these into objects instead of just user data. Again, metatables are tables that can be used to change the behavior of tables or user data. Everyone probably is aware of some of this. In this case, we're using it to assign a type to our user data. And our metatables also hold all our mappings for all the methods on the objects. Okay, this is just a shortened version of the class structure that's used in Gemini for the ObjectiveC. And most of you probably don't care about ObjectiveC, but basically you have a base class of gem object. Everything inside Gemini is a gem object. And then you have display objects and other classes derived from gem object, but all the graphical elements are gem display objects. But the gem object itself is actually where the connection to Lua is happening. And I don't want to bore you too much with ObjectiveC, but I wanted to show this just because if you look at the interface definition there, you have 4 different properties that are of interest to as far as Lua goes. One is the Lua state is stored with the object because the object can only exist in one Lua state, and Gemini only uses one Lua state for everything. There's 3 references there. Self-reference, which means the object actually has a reference to its corresponding Lua object stored internally with it. so that it can actually refer to itself at times. There's a property table ref, and I'll talk about that, which is basically just a reference to a table that allows people to arbitrarily add data to their objects. And then there's event listener table ref, which is a reference to a table that stores all the pointers to the event listeners that are set up for this particular object. So if we look at the initializer for this, the first thing that happens when we create any object in Gemini through Lua is that it's going to create this gem object, and the first thing it's going to do is assign its Lua state to whatever Lua state was passed in, and then it's going to create an object. Then it's going to create a user data space in order to store the pointer for this particular object that's under creation, and then store itself in that user data. Next thing it's going to do is get the meta table for whatever type of object was you're asking for. Again, the gem object is the base class, so this initializer gets called by all the other classes that are created. So for the rectangles and things like that, they're going to say, okay, initialize an object of this type, and they're going to pass in a string key that says, this is my type. So at this point, you grab the meta table for that particular type, and then you set it as the meta table in this user data. Next thing you're going to do is create a Lua table that's going to be used as the user data for this. As the user value for this user data. This allows us to arbitrarily, after we create, say, a rectangle or a circle, it allows us to set our arbitrary attributes on it. So, for instance, if you have a sprite and it represents a character, you may want to store the character's hit points on it. You can just simply say sprite.hit points equals 100, and it'll automatically create, add that variable to the object. So all the Gemini objects can be extended that way. And that's what this table does. So you store that as the user value. And then we also create a table to store event listeners, because you can add event listeners to every object in Gemini. For instance, if you want to listen for touch events, you can add touch handlers to receive the touch events. And this gets stored in this table here. And then the last thing we do, and this is probably bad practice, but it was very convenient, is we're just going to basically leave this thing on leave this user data on the stack, because this is getting invoked from Lua when someone calls a factory method in order to create an object. And so the last thing it does after it creates itself is leave its user data on the stack, and that gets returned as the object. In retrospect, it's probably not the best design to be this tightly coupled with Lua, and it does create some problems, but it was very convenient, and so it made it a lot easier to do certain things. But it may change in the future because it makes it harder to do other things. All right, the libraries consist of two types of functions, basically. You've got the library functions, which are factory methods and methods that affect the global state. So these are methods you're going to call directly on the library itself, either to create a new object or to set the global state to something else. Oh man, looks like I'm running a little long here. And then the other type of functions you have are all the object methods for whatever kind of object you're creating. For instance, if you want to, the set field color, any object method you would invoke would be defined in these libraries as well. All right. All right. So I probably got about 5 minutes left, right? All right. Well, let me just then move on to some demos. So you can see what I'm talking about here. There we go. All right. Okay, in this first level, just showing some simple physics, showing you a bunch of different shapes going on here. The star is being rotated with one of those enter frame event handlers, and the circle and the red circle and the two squares at the bottom had simple physics. The green sides there are static backgrounds that don't let things penetrate. That was a transition. That was a slide transition moving up. This is another. This simple windmill thing uses grouping to group the rectangles in the middle, the red rectangles and the blue rectangles in the middle to make the blades of the windmill, and then uses another event listener, another enter frame event listener, just to spin it whenever each frame event happens, each enter frame event happens. What happened here? Okay. This scene, this level is just about 350 or so Mario sprites running around, just to give you an idea of the scalability. I've been able to do many more than that. I think I lost count around 700 or 800, and still get 60 frames per second. So there's a lot of effort went into setting up sprite batching and making this all happens with one draw call to make the sprite rendering as efficient as possible, because that's obviously the most important thing with most 2D games. Here's some more sprites here. On this level, I'm showing the hybrid drawing mode. Sometimes it's useful when you're debugging your physics to be able to turn on a debug mode so you can see the physics shapes that are attached to your bodies. In this case, our little sprite guys fell down. The green polygons layered on top represent dynamic bodies, or fixtures that are attached to the body. The blue represents sensors, and the red are static bodies. Okay, this isn't just another simple physics demo that's got terrible artwork and a little bit of interaction. If I touch the cannon there, we get our little cannon effect. And if I had sound through this, you would have heard the boom. But again, this is using just simple physics set up for the boxes. They're dynamic. The cannon's a sprite, and a little ball was just a circle. This level shows a little more interactivity. Again, it's using physics to control things. I got my Mario here, and I want to get off to the side, but can't get over the wall. Maybe if I grab that coin, it'll help, but can't get up there. So, whoop. Oh, there we go. Okay. So this is using a lot of the different things we talked about. Physics for all the elements. You see the background is just simply another big sprite. Mario is a sprite with physics properties set on it. And then collision detection using a collision event on that coin. When I touched it, it triggered an event handler that then lowered the wall there so I can get past it. All right, well, that's Gemini.